All right, this video for 5.3 is not going to be nearly as long as finishing up 5.2. This is over the natural exponential function. So we're going to talk a little bit about the number e. This is Euler's number, E-U-L-E-R. He was a mathematician. Euler's number. Oops, I misspelled number. Also called the natural number. It's called the natural number because it shows up in a lot of natural growth situations. The number e is kind of like pi. Pi, is about 3.17, and then we could go on from there, on and on and on. Natural number, Euler's number, similar idea. It was discovered, much like pi was discovered. And e is approximately 2.71828. If you type in e into your calculator, sometimes you have to put in e to the first because it only pretty much gets used with exponential functions. It'll give you the decimal approximation there. We use this with continuously compounded things. So we talk about continuously compounded interest with money, but there's a lot of natural growth and natural decay situations. So when we look at radioactive substances that decay, or the way different populations will grow or decay in the wild, we see this natural number show up. So for continuously compounded interest, the formula for that is A, our final amount, equals P, our principal, times E to the R times T. R is our rate, and T is our time. All right, two different problems here to practice using the continuously compounded interest formula. Notice it says when Amy was born, her grandparents deposited $5,000 into a college savings account. So here's our principal, our starting amount, paying 4.6% interest. So this is where we're going to get our rate from. Compounded continuously. So we're going to use the natural number, E. What will the balance be when she graduates at age 18? So there's our time. So A equals our starting amount, principal of 5,000, times the natural number E raised to the power of 0.046 multiplied by our time, 18. From here, we just take it and pop it into our calculator. If you want, you can multiply the exponents parts together. That would be 5,000 times e to the power of 0.828. And when I put that into my calculator, 5,000 times e to the power of 0.828, I get $11,443.68. I want you guys to go ahead and pause the video and try the second one on your own. All right, hopefully you have all your substitutions made and you're ready to check your final answer against mine. You should have gotten $14,294.95. Fantastic. Let's do some more word problems. All right, so on these word problems, anything is fair game. It might be using E, the natural number. It might have a different base. All right, we're going to write the law of growth and decay formula first, though. The law of growth and decay formula, f of x is equal to a. That would be my initial or starting amount, my y-intercept. Times e, the natural number, Euler's number. To the kt. T is time. And k is the constant of growth or decay. If it's decay, our constant is going to be a negative. If it's growth, our constant is going to be a positive. So that constant of growth or decay for every substance out there that either grows or decays using this natural number E, that each individual thing is going to have its own constant of growth or decay. All right, so let's read through this word problem. Atmospheric pressure. The atmospheric pressure, P, on a balloon or airplane decreases with increasing height. The pressure, measured in millimeters of mercury, is related to the height, h, measured in kilometers, above sea level by this function right here. pH is equal to 760 times e to the power of negative 1.45 h. So there's a couple things that I know about this. Here's the initial height. Or sorry, not the initial height. That would be the initial pressure. My apologies. Initial pressure. I know this is showing me decay because this is that constant and it is negative. So this is a decay constant. If it was positive, then it would be a growth constant. All right, find the atmospheric pressure, so we're looking for P, at a height of 2 kilometers, which is over a mile. And notice in the problem, my height is being measured in kilometers, so I'm just going to take this and substitute it in. I have P, and then 2 kilometers is equal to 760 times e to the power of negative 0.145 multiplied by that height of 2. I'm going to take this, I'm going to pop it right into my calculator. You can multiply that exponential part together first if you want to. If you multiply that exponential part together, you would get, sorry, get my pen here, negative 0.29. So pop that into your calculator, and you find the pressure at 2 kilometers is, we're going to round this to 2 decimal places, 568.68 milliliters of mercury. Whenever you have story problems, you need to have units on your answer. Part B, almost the exact same process. Actually, it's the exact same process. We're just using a different value for H here. So the pressure at a height of 10 kilometers, 760 times E to the power of negative 0.145. This time we're going to substitute in 10 in the place of the height. You can pop it in your calculator just like this. If you want to simplify that exponent first, you may absolutely do so. If you decide to do that, that would be negative 1.45. So I do 760 times E times to the power of negative 1.45. And I get that the pressure at 10 kilometers is right about 178.27 milliliters of mercury. Please, please, please make sure you are including units on any kind of story problem. All right, I want to look at just a couple more story problems with you, and then 2 more solving problems. We've got depreciation and drug medication. So for depreciation, the price P in dollars of a Honda Civic EXL sedan that is X years old is modeled by this function right here. P of X equals 22,265 times 0.90 to the power of X. So here is the initial price, the new car price. And I can tell from this 0.90, because that's smaller than 1, that this is decay. It's going to be losing value. How much should a 3-year-old Civic EXL sedan cost? So we are going to take 3. We're going to substitute that in for X, and we will find what the price should be. So P of 3 is equal to 22,265 times 0.90 to the power of 3. Pop that in your calculator. We are going to round this to the nearest cent. I got 16,231 and 19 cents. Go ahead and do part B on your own. Do part B on your own. We're going to round this one to the nearest cent as well. Here we put 9 in the place of X, because that is our measurement of time. You should have gotten about 8,625 and 92 cents. All right, last piece of this question. Last piece right here. Explain the meaning of the base, 0.90, in this problem. So the meaning of that base, the car retains or keeps 90% of its value each year. So if it is keeping 90% of its value each year, how much is it losing? Keeps 90%, so it loses 10% of its value each year. All right, drug medication. The function d of h equals 5 times e to the negative 0.4h can be used to find the number of milligrams, d, of a certain drug that is in a patient's bloodstream h hours after the drug has been administered. So how many milligrams will be present after 1 hour and after 6 hours? Couple things that I can tell from this formula, because the 5 is in front of the E, the initial amount is 5 milligrams. So I know that this patient is taking 5 milligrams initially. I also know that it is decay because we have that negative 0.4 times our time. So we're going to do this for both 1 hour. That's going to go in for H. And we're also going to do this for 6 hours. So even though it doesn't have a part A and a part B, we're really doing a part A and a part B. So the amount of the drug left after 1 hour would be 5 times E to the negative 0.4 times 1. That's very easy to simplify. In my calculator, I'm going to put 5 times e to the power of negative 0.4. We're going to round this out to 2 decimal places, I think. That would mean about 3.35 milligrams left after an hour. Same process. Try that for 6 hours on your own and then check your work against mine. Same exact process for 6 hours. So when I do 5 times e to the power of negative 2.4, take this out to 2 decimal places, I get about 0.45 milligrams after 6 hours. All right, 2 problems left that I want to do with you guys. And then we're all finished up with 5.2 and 5.3. This is similar to the problems that were at the end of the 5.2 video. I want to find a way to write each side with the same exact base. So then I can just be looking at the exponents and solving for the exponents. I have E, and E here, but this last E is down in the denominator, so I'm going to rewrite that last E instead of 1 over E cubed. I'm going to write that as E to the power of negative 3, and then I'm going to use my power to a power rule right here. E to the x squared, That is going to be e to the 2x because I multiply those two together. All right. Over on the right, same base, and they're being multiplied together. So I'm going to take those exponents, and we are going to add them. I have the same base on the right-hand side too, so I'm really just going to be recopying those exponents and working only with the exponents from here on out. So I have negative x squared equals 2x minus 3. First thing I notice about this, of course, is that x squared. That means this is quadratic. And to solve quadratic functions, we are going to set that equal to 0. And then we are going to factor this. I always want my x squared to be positive. Right now it's a negative x squared. So I'm going to add x squared to both sides. So I have 0 equals x squared plus 2x minus 3. So I want to factor that. Multiplies to negative 3, adds to a positive 2. That would be 3 and negative 1. So I'm going to have x minus 3, or sorry, x plus 3, my bad, because it was positive 3. X plus 3, x minus 1 are my factors. And so my solutions here are going to be x equals negative 3 and x equals positive 1. Just like with the other problems, you can take that and substitute it in, check it out in Desmos, make sure that that actually works correctly. See if you can do number 2 on your own. Go ahead and pause the video right now, see if you can do number 2 on your own, and then check back with me. All right. For this last one, use your power to a power rule. So you get e to the 4x. And then we have e times e over on the left. So I'm going to add those exponents together. So 4x plus x squared. I have a base of e all the way across. So those bases literally just kind of drop out of the picture. I have 4x plus x squared equals 12. We have a quadratic equation here because of the x squared. So that means setting it equal to 0 and factoring. So I get x squared plus 4x minus 12 equals 0. Multiplies to negative 12. Adds to a positive 4. That's going to be 6 and negative 2. So x plus 6, x minus 2. That means x is negative 6. X is positive 2. That finishes up 5.3. Please let me know if you guys have any questions. Send me messages in Canvas. I am more than happy to answer any questions you guys might have. Have a good one, and I will see you guys tomorrow. Bye.